My name is Soham Roy, and I am a PhD candidate of Electrical and Computer Engineering Department at Auburn University in Auburn, Alabama, USA, under the supervision of Professor Spencer Millikan and Professor Vishwani Agarwal. Today, I am going to give you some prior work and motivation for this study. Then, I will explain how machine intelligence is applied to our study. I'll also discuss about the possible directions leading to a formal training procedure of the artificial neural network. I'll then discuss on how we resolve conflicted training data patterns using some trivial mathematical calculations, followed by the proposed recursive training algorithm which makes our ANN an evolving ANN. I will also analyze our experimental results thoroughly. Finally, I will conclude this talk by briefly point out the major contributions of this study and future avenues that may be taken to achieve more interesting results. The Dee algorithm in 1967 established ATPG as a standard method of generating high-quality tests for the logic circuit industry. However, since its introduction, it was noticed that ATPG can have frustratingly long runtimes for some circuits. Numerous later studies lowered ATPG runtime, a major contribution, but since the introduction of BODEM in 1981, the theoretical upper limit of ATPG runtime has remained constant. Let us see an example. For a circuit with I inputs, these I may include scan latches in case of scan-induced circuits. ATPG may need to simulate 2 raised to the power number of primary inputs of the circuit vectors to find a test. Although ATPG algorithms typically find tests without simulating close to this many vectors, this upper bound still exists and is occasionally seen in modern circuits. To avoid this upper limit, most ATPG algorithms employ backtracing subroutines. These subroutines trace backwards through a circuit starting from an objective, such as exciting or propagating a fault, and attempt to find input assignments which accomplish the objective. Multiple backtraces from an objective may be required to meet the objective. But if these input assignments accomplish the final goal, that is find a test for the fault, then at most I input vectors must be simulated, which is nothing compared to the theoretical maximum of 2 to the power I. However, this ideal situation presumes no backtracks occur during ATPG. When the backtracing subroutines reach a circuit input and assign it a value, this assignment may block the current or future objectives. When this occurs, ATPG must undo or backtrack to some previous assignment, which means ATPG wastes time simulating unnecessary input vectors. Beyond BODEM, numerous ATPG algorithms attempt to reduce runtime by creating fewer objectives, but to our knowledge, no studies compare ways of backtracing from an objective. When backtracing, it must decide which direction to go, but choosing a wrong direction may result in a backtrack. To develop a new backtracing strategy, I look towards the technology of machine intelligence. Machine intelligence describes a broad category of algorithms that automatically program themselves through experience. This experience can come from unclassified data which the program finds patterns in, which is unsupervised learning, or the experience can come from a database of training problems with desired outcomes, which is supervised learning, or the experience can come from iterative re-evaluation and adjustment, which is reinforced learning. Recently, International Test Conference ITC 2020 published our research work, which shows that an artificial neural network ANN can combine multiple heuristics to guide an automatic test pattern generated ATPG with fewer backtracks than required by guidance from any single heuristic. We are going to reuse same ANN structure that has a single output neuron and a single layer of hidden neurons, which is sufficient to accommodate the training data volume. Conventional BODEM ATPG applied to hard-to-detect and easily detectable faults in selected benchmark circuits provide training data for nodes marked as success if the backtrace leads to a test, or failure if it results in backtrack. Each entry in the training data pattern comprises of the COP controllability, the circuit depth, and the driving gate type given as a one-hot string on the decision point. Let us try to figure out the motivation of this study. These are the results we obtained from our own work of ITC 2020. Since results depend heavily on benchmark sizes, we chose to normalize plots with respect to ANN-guided backtracing results, which we believe more accurately reflect the goal of ATPG research, that is, to reduce ATPG runtime by a factor as opposed to by a constant. Therefore, positive plots in these figures reflect results favorable to the machine intelligence. The results on decreasing backtracks show promising results. we see that for most benchmarks, using the ANN in lieu of conventional heuristics decreases the number of backtracks, often considerably so. As we can also see that the improvement in ATPG performance for some benchmark circuits, including some larger benchmarks such as C3540, C7552, C2670, and C432 did not perform well. To motivate this work, we repeated the work of ITC with minor changes. Firstly, training patterns were generated using PODEM applied to 100 hard-to-detect faults in the three highest depth circuits, that is C6288, C3540, and B05. Secondly, the trained ANN was then used to guide a PODEM applied to the 100 hardest to detect faults in each of the 24 benchmark circuits used in the original ANN, that is ITC studies ANN. This figure compares the total backtracks with those of conventional PODEM using distance and COP heuristics. One difference in our evaluation procedure, as stated in the ITC study, is that we did not include backtracks from aborted faults. We refer ITC studies ANN as the original ANN to distinguish it from the ANN developed in this study identified as the new ANN. The ANN training in the ITC research study was ad hoc and rudimentary. Therefore, this study provides a formal training that may elevate ANN-guided PODEMs at performance. This study examines such a training method. The training recursively uses ATPG data generated from hardest to detect as well as easily testable faults, resolves conflicts in data patterns, example when different ANN outputs come from similar inputs, and discards data that does not improve the guidance of ANN. We believe remedying the outliers just mentioned a few slides before requires addressing several aspects of the ANN training procedure. Our investigation led us into following observations. Firstly, the ANN was trained with ATPG data from high-depth circuits. Since C3540 causes worry, I retrained the ANN with just C3540, but still the ATPG performance of this circuit did not improve. Therefore, I retained the three high-depth circuits for training. Secondly, the training data patterns may lead to increase in training error of the ANN and thus degrade its guiding ability. This is explained in details in upcoming slides. Thirdly, all faults do not provide useful training information, and pre-selection of faults for training may unnecessarily increase the training data volume without benefit. Upcoming slides gives a novel method of training the ANN considering three aspects. That is, the training error of ANN must be kept low by adjusting the number of hidden neurons. Training data from a fault must be accepted only if guidance from the resulting ANN reduces backtracks, and the faults used for training data generation should not restrict it to be hard to detect faults. In fact, a fault provides useful training data as long as it reduces backtracks. And finally, the ANN may enter a zone called catastrophic forgetting when it forgets information contained in a large training data volume. Such consideration in training improvement is worth exploring in the future. To remedy conflicting training data patterns, we collect patterns with identical features into groups and then replace each group by a single representative pattern with common features. Since these patterns are derived from actual ATPG runs, the label of a pattern is either 1 indicating success if it belongs in a backtrace leading to a test, or 0 indicating failure if it results in a backtrack. We count the number of 1 and 0 labels in the group, and the representative patterns label is given in the next slide based on a formula. In this slide, a conflict is illustrated by the sample training patterns in figure where the first three patterns have a conflict. This is resolved in this figure where the three patterns are replaced by a single representative pattern with a label count equals 1 divided by number of label 1s plus number of label 0. That is 2 divided by 2 plus 1 equals 0.67. The algorithm is to develop an evolving ANN guided ATPG is illustrated in the figure. We select large depth circuits C6288, B05, and C3540 from ISCAS 85 and ITC 99 benchmarks. The ANN structure is same as in the ITC recent study, and parameters such as number of hidden neurons and mean square error are initialized. COP-based PODEM is applied to a set of 100 hard-to-detect faults, and number of backtracks is recorded to be minimized through recursive learning. The training starts by using 50 hard-to-detect faults to generate a training database, followed by ANN training to check mean square error and record the corresponding number of hidden neurons simultaneously. This process continues until mean square error starts saturating and corresponding mean square error and the number of hidden neurons are recorded and the ANN is retrained. The similar process is continued for 100 easy-to-detect faults. To evaluate the training, the ANN-guided ETPG is applied to 100 hard-to-detect faults of the same training circuit. If backtrack count decreases, then 100 more hard and easy-to-detect faults are added to the training of the ANN as the number of hidden neurons and mean square error are restored. Discarding the corresponding training patterns from the training database, and another circuit is selected to reiterate the same process until one of the following conditions is satisfied. We kept these conditions to satisfy our need, but one can always change these conditions. These conditions are: the number of backtracks should be reduced to at least 50, at most 100 hard and easy to detect faults should be used for training, and finally the ANN contains at most 100 hidden neurons. The graph shows how the new ANN performs on 100 hard to detect faults across benchmarks as compared to the original ANN. In terms of backtracks, with few exceptions, the new ANN does the same or better in reducing backtracks compared to the original ANN, especially for larger circuits. This experiment used all faults, that is testable and redundant faults, to show the efficacy of guidance by the new ANN using the proposed training procedure. Clearly, the new ANN performs better with fewer backtracks than the original ANN as shown in graph, reaffirming the value of the proposed training technique of this study. The graph has some notable observations. First, C17, B02, and B01 have no reconvergent fan-outs and therefore have no backtracks. Of course, there is no scope for reducing backtracks by new ANN guidance. Second, except C1908, C432, C499, B12, and B05, the new ANN exceeds expectations in terms of back performance based on reductions in backtracks. Third, the new ANN is able to reduce backtracks for B09, but the CPU time increases. Possibly more time per backtrace is used in order to reduce backtracks by expensive evaluation of weights and biases of ANN edges that involves matrix multiplication and computation of sigmoid function. Fourth, the new ANN heuristic does not perform as well on a few circuits compared to the original ANN, but it still outperformed the conventional heuristics like distance and COP, except in case of C432. Here in this graph, it illustrates that CPU time remains constant for smaller circuits, and reduction for high-depth circuits is observed, perhaps due to simultaneous reduction in backtracks and backtraces. The contributions of this study are listed. Firstly, a technique to resolve conflicts among ANN training data. Main benefit of conflict resolution is improved ANN accuracy as evident from reduction in the mean square error during training. Secondly, a training technique for selecting faults using a recursive training method that
Hello?
Hello. Hello. Am I audible?
Yeah.
Yeah.
Yes, you are.
Yeah. The presentation was very beautiful. I just have one question regarding this. So I wanted to know what is ATPG.
So ATPG is an electronic design automation method. It's a technology used to find an input sequence that, when applied to a digital circuit, enables automatic test equipment to distinguish between the correct circuit behavior and the faulty circuit behavior, which is caused by defects.
Okay. Okay. Great.
Yeah.
Yeah. Thanks. Thanks. Okay. I don't have.
Good morning, everyone. I am Firaz Hussain. It is my honor to present my research work in the 34th International Conference on VLSI Design. My topic of presentation is a zero point 0.4 microampere offset 6 nanosecond sensing time multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology. Authored by Faraz Hussain, Bilal Iqbal and Dr. Anuj Grover. Since every research is built on motivation, we are not apart from it. Physical limitations in scaling of non-volatile memories necessitate alternative ways to increase on-chip storage density. And new generation NVMs offer advantages in terms of speed and can enable replacement of embedded volatile RAMs. Further, storing multiple bits in a single cell enables reduction in cost per bit. Therefore, we studied various essential sense amplifier design techniques such as offset voltage cancellation, double sensing margin, strong positive feedback, etc. to achieve a parallel sensing multi-level sense amplifier for resistive non-volatile memories with faster and stable read operations. First, I will cover basics of the offset cancelling current-based sense amplifier, then design of the enhanced OCCP SA. Thereafter, multi-level sense amplifier design for resistive non-volatile memories, followed by comparison and conclusion. Offset cancelling current-based sense amplifier involves two-phase sensing operation. One is pre-charge phase P1 and second is amplification phase P2. At the beginning of pre-charge phase, switches S1, S2, S3 and S4 are turned on while two switches DS1 and DS2 are off. The diode connected transistor M1 and M2 provides precharge current I pre1 and I pre2 to the bit line and dummy bit line along with ICEL and IREF. Despite the process variation in M1 and M2, current IM1 and IM2 becomes ICEL and IREF after enough precharge time. At the end of P1, cell voltage V cell and reference voltage V cell are stored in capacitance C1 and C2 respectively. In the amplification phase, the four switches S1 to S4 are turned off while two double sensing margin switches DS1 and DS2 are turned on. The introduction of these two switches serves as data dependent reference generator and generates strong positive feedback. The transistor M1 charges this node V cell with the current IM. At the same time, the switch DS1 will discharge this node V cell with the current IREF. Therefore, the total current difference between node V cell and node VREF will be twice of delta I, where delta I is difference between I cell and IREF. Simulated waveform for the case when I cell is less than IREF is shown in the figure. When ICEL is less than IREF, it leads to an increase in VREF that causes lowering of IM1 due to AC coupling behavior of C2. Eventually, this IM1 lowering leads to a monotonic decrease in V cell, which is shown in this figure. Hence, a combination of double sensing margin and strong positive feedback in OCCP assay result in a faster sensing time. The presence of device mismatches M1 and M2. Here we are explaining this high read stability using case when the reference current is greater than the cell current. In precharge phase, current IM1 should be smaller than IM2 in the absence of device mismatch as shown in figure number 3b. Here IM1 is smaller than IM2. However, in advanced technology node, there will be process variations which may lead to a larger IM1 and hence incorrect current sampling in precharge phase as we can see in figure number 3b. Now at the beginning of amplification phase, V cell starts to decrease because of the discharging current IREF flowing through the switch DS1 And finally, effect of the strong positive feedback decreases cell voltage vessel till ground. So the wrong current sampling during pre-charge phase due to the device mismatches will be corrected by the OCCP assay. While state-of-the-art OCCP assay we examined so far offers very prominent merits, but it suffers from the power overhead caused by a clamp voltage, which gets aggravated in multi-level sense amplifier design. So we propose a new current sense amplifier structure which is known as enhanced offset cancelling current based sense amplifier, and down the line we will be using the word EOCCB SA, which is combined with a voltage latch sense amplifier that is shown in figure number 4. We can see signals pre and amp have been introduced to control the switches S1 to S4 and DS1 DS2. The voltage latched SA will be enabled by signal SAEN and used to generate the digital signal either 0 or 1 based on the EOCCB SA output VCEL and VREF. The consolidated sensing time Tsn of the proposed EOCCB SA is given here, where T pre and T amp is the precharge time and amplification time of the EOCCP assay, while TSAN is the time during which SAN signal is enabled. For clarity, we a complete sequence of the signal associated with the circuit is shown in the figure number 5. The design has been implemented at 1 volt in 65 nanometer LSTP technology, and 4000 Monte Carlo runs have been done across the entire range of PVT conditions to characterize the EOCCB assay. We ensured the design robustness until 0.85 voltage while keeping the sensing time of 6 nanoseconds. In pre-layout simulation result, we noticed that the EOCCB assay has very low 3 sigma offset for a very wide range of current, that is from 20 microampere to 70 microampere. This is significantly better than other state-of-the-art current sense amplifiers. The EOCCB achieves a minimum of 3 sigma offset of 0.4 microampere for reference current 27 microampere, whereas sensing time is 6 nanoseconds. We designed the layout in a common centroid topology and recharacterized our design. The comparison of pre-layout and post-layout result is shown in this figure number 7. It is evident that the low offset range as seen in the pre-layout result has been maintained in the post-layout analysis, and it achieves same yield as offset cancelling current sense amplifier without a clamp.
Hello?
Hello?
Yes, the floor is open for questions now.
Yeah. So I have a question. What is ANN?
ANN, or as we know, artificial neural network, is the piece of a computing system designed to simulate the way the human brain analyzes and processes information. It is the foundation of artificial intelligence, known as AI, and solves problems that would prove impossible or difficult by human or statistical standards.
Okay. Okay. Yeah, so I think I got my answer. This is the great significance you have explained of ANNs. Thank you very much.
Thank you so much.